Hi, everybody, and thank you for being here. I'm part of a research group inside the University of Bolzano that is working on machine learning, but I come from a previous experience in signal processing, and so in this research project, I'm trying to combine things and put all the knowledge together in order to have something useful to use for students and also for the community. What is NIME? NIME is an open source platform by means of which you can do codeless programming of machine learning tasks. So it's intended for a use both of an expert, but also for people that don't want to care too much about coding and stuff. It has a different set of nodes. You can see them here, by means of which you can create easily a graph of processing and define what is the set of operations that you want to do inside your data. Originally is intended for textual data. And the objective of this research project is about introducing a new set of nodes that are dedicated to the processing of images. So we started from the very beginning because there was an original version of the nodes dedicated to image processing, but was not maintained properly, and now we have new libraries and new possibilities. Moreover, NIME introduced the possibility to implement new nodes using Python. Originally, NIME is written in Java. And thanks to this, we had the possibility to reuse part of the software that we commonly use during a standard image processing pipeline. The objective, of course, is to do image processing, to extract feature, and then go for machine learning, classification, and more advanced tasks about this processing. So initially, we developed a set of nodes dedicated to standard denoising activities like mean average filters or the raw filters. And we went for equalization or for standard edge detection system like Sobel, Roberts, or Laplacian. And finally, region detection methods. So standard methods that are intended to process the image, to clean it, prepare it for processing, so denoising and equalization, and extraction of mid-level features like the edges, the contours of objects, and the regions. The current development of nodes is this one. We have a set of nodes dedicated to the loading of images. For the time being, we are able to work with JPEG and PNG images. We are not able actually to work with Deacon images, for example. We are doing denoising and edge detection, and we are open also to new collaboration. So if somebody wants to join our group and develop a node, I'm always saying also to students, if they want to do a nice project on that, we are very glad about this. So the pipeline for image processing can then be transformed into a set of nodes reading a list of 5, because we suppose that somebody looking for some properties of images is interested in processing a set of images, not just one. And then we transform data so that we can then apply the different things and eventually evaluate the different levels of extraction. Here I show you a simple application. It's just an application is not intended to be used inside a real medical situation, but it's just to demonstrate that it's possible to use it to work on images like this one. So we have noisy imaging because of many things, because of noise present in the pipeline, because of low level of exposure that we want to use during the acquisition of the images. And thanks to the possibility of this pipeline of codeless programming, you can try to improve it, first applying some denoising, standard denoising, and eventually go for equalization, and eventually go then for edge detection. So here you have the set of images starting from, the noisy one, here you have the denoised one, then the equalized, and finally you have the edges. Then the point is go ahead with other kind of technique exploiting the feature extracted. So this is done thanks to the implementation also with Python and OpenCV. OpenCV is still open source, so we maintain the status of the nodes that we are developing. Different kind of technique led to different levels of quality. There are different techniques that are able to show different properties of the image. So this is the reason of having a different kind of implementation. So what if we go ahead and we try to include other kind of possibility offered thanks to the development of artificial intelligence and to the introduction of the artificial intelligence inside the pipeline of image processing? So we try to include inside the nodes available to the user also an implementation of the very well-known YOLO and Segment Anything Medical that are two reference AI that can be exploited to extract regions inside images and classify them. Both have an open source license. YOLO somehow is less, let's say, open source in some sense in the last version because of collaboration with Ultra Analytics, while Segment Anything is released under Apache version 2, so you can use it without many problems. And we experienced some, let's say, we implemented some simple workflow so that we can demonstrate what is the use of this AI on standard problems like object count or segmentation of regions. Here I show you an example of pipeline. So you read the files, you transform it into strings, and then you load the images, and finally you just go for a YOLO. The model of YOLO is downloaded by the user. If the user has experience, can create a model targeted to his problem. So you can do by yourself retraining or fine-tuning or whatever is needed by the activity, and then use the weights and the model inside the node. Here I show you a very simple example of segmentation with one of the images of the website of the University of Bolzano. So YOLO is able to quickly detect regions and objects and give a classification with many categories. Around 50 categories are available in the standard version. But the interesting thing is that from the standard library, we can detect both bounding boxes of objects and also the real coordinates of the objects that are inside the region. So it's quite easy to think about some problem of application. We tried it with a standard problem of classification, not because we are not trusting YOLO, but we want to test our implementation using KNIME. So this is a benchmark that can be easily be implemented using synthetic data to detect a box of Cheerios inside an environment. And the objective here is to train all the data set with synthetic data and then identify the real objects that are inside the test set of the images. This was intended also to have an idea using standard images if it is possible to work with artificial intelligence and also synthetic data in order to solve a problem. We have some cases of synthetic data in various environments, but also inside the medical environment. We start to have some synthetic data to generate situation, to generate particular conditions that are not easy to be found in reality, or they are not possible to be found. This is the pipeline. So it seems like it's just a cycle of node, and it's easy to get, in the end, the possibility to evaluate your result in terms of the quality, see some example, where it's working, where it's not working, and so on. Lastly, we can, of course, generate some plot of the results in terms of accuracy so that we understand how good is the model in the performance. The last implementation that we did is to implement a version of Segment Anything Medical that is intended to understand better what is the content of a medical image. And we just finished some weeks ago, so we don't have a big expertise in a big set of data on that, but we tried it on a set of medical images coming from Kaggle about breast lesions. So in this field here, we'll build up, what we build up is the part related to the use of segment anything, that is this automatic segmentation module here, and combined with the ground truth, we evaluated the possibility to execute it on the images that are given inside the data set and detect what is the mask for the activity that we are looking for, and finally try to overlap what is the result on the original image. So this is working very well when you have the possibility to identify a first region that might be interesting inside the image. Basically, it could be a radiologist saying, in this region I see something strange, and then let the tool automatically identify the dimension of whatever is seen. So I don't think that none of these tools can be a substitute of the radiologist expertise in identifying things, but can be of help in some situation when the radiologist is tired, of course, but also when he's looking for something else. So I'm doing a CT scan because I had an accident and they are looking for some disease related to the accident, but eventually there are some secondary disease or other kind of things that are not be evidenced because they are not under investigation. So if you have the possibility to automatically process these images also overnight and eventually pick up to the radiologist just the cases where it seems like there is something else, this could be, I think, useful. And that's all. This activity has been developed inside the laboratory. I'm just the speaker of the laboratory. There are various people collaborating, namely Ali Bhatti and Thomas Borsani, and also Professor Di Fatta, who is the head of the laboratory. Here we have a GitHub about the project. We are releasing the version of the software that we are doing, and soon there will be the community extension inside the NIME platform. Thank you.
Thank you very much. We have time just for one question.